Okay, so now that we've done some basic set theory and basic logic, we head into the main meat of the course, which is we're going to learn how to prove a bunch of stuff. Okay. And the first technique that we're going to learn is a technique called direct proof, which is section 3.1 in your textbook, but I'll be sort of doing something a little bit different from your textbook. So I'll explain what I mean by that later on in this lecture. So it's not exactly like section 3.1 in your textbook, but it roughly corresponds. Okay, so what is direct proof? Direct proof is sort of the most basic proof technique. Okay, so in a direct proof, use a direct proof to prove a conditional if P then Q. Right, so if n is even, then n squared is even. How do you prove if n is even, then n squared is even? Well, one thing that you can do is you just assume that P is true, you do something, and then you show that therefore Q must be true. That would prove that this conditional is true because anytime P is true, Q must be true. So the technique of direct proof is 1, you assume that P is true. Okay, 2, I'm going to write magic here. And 3, you deduce that Q is true. Okay, so I put magic in step 2 because depending on what you're trying to prove, you will do different things in step 2. But what goes in this magic? Let's say, i.e., simple deductions using things that we already know. So as long as the things that you do in step 2 are things that you know are true, and if you start by assuming that P is true, you do a bunch of stuff that you know is true, and then you show that Q is true, then you've shown that the conditional if P then Q is true. Okay, which brings up an important point, which is that in order to prove any statement in mathematics or in general, you have to start with some things that you already know are true in order to do the magic. Right? So in order to prove anything, we must start with things we know are true. Otherwise, we can't get anywhere. So what are we allowed to use? What are we allowed to start with? Okay, so there's 3 things that you're allowed to assume are true when you're writing a proof. Okay, so 1 is you're allowed to assume any basic definitions. By this, I mean, right, and definitions given in class. So for example, we've defined a set, so you're allowed to use the definition of a set in your proof. You're allowed to use the definition of a subset in your proof, right? That's another thing that we defined in section 2.3. Right, we said that A is a subset of B if whenever X is in A, we must have X is in B. So you're allowed to use that definition in your proof. You're trying to show that A is a subset of B. You say, well, suppose that X is in A. I showed that X is in B, therefore A is a subset of B. Okay, so any definitions, we're allowed to start with that. So for example, the definition of a subset. Or we're allowed to say that any even number is an integer. Let's say uneven number is an integer that can be written as 2 times k for some integer k. Okay, this might be the first time I'm giving you this definition, but this is a basic definition, as in when I say the word even number, this is what I mean by the word even number, by the phrase even number. So if the proof was suppose that n is prove that if n is even, then n squared is even, we can say, oh, well, suppose that n is even. Therefore, by definition, n equals 2k for some integer k, because that's the definition of an even number. Okay, so you're allowed to assume basic definitions. You're also going to be allowed to assume properties of the real numbers that we will assume are true. These things are called axioms. Okay, so an axiom is just a statement that you assume is true from the start. It's like the foundation of your mathematics. You need to start somewhere, so we'll start by assuming a bunch of stuff is true. Okay, so there is a whole sheet that I will give you here. Hopefully you can see this on screen right now. With a bunch of axioms. You will be able to always assume these axioms in any proof. Also, on your homework, you will sometimes be given problems where you can only assume these axioms. I'll also provide this sheet for you, I guess, on exams, although our exams are online, so yeah, you'll have it on your computer. Okay, so this will be uploaded to Canvas, but I will go through all these axioms explicitly in this lecture as well. I still recommend that you actually write them down so that you can process them, but you'll get this PDF. I'll post it to Canvas. Okay, and then the third thing that you're allowed to use, unless the prompt says otherwise, is anything that we've already proven. Either in class or on a problem set. Right, so if we've proven some result is true, then you're allowed to use that result, as long as at some point you've written down the proof. So that means in class or on a problem set. Okay, so as I said, we'll go through carefully all of these axioms of the real numbers that we're going to assume are true to start. Okay, so axioms of the real numbers. Okay, so this I think is not in your textbook. I'm borrowing these axiom sheets from Professor Ostroff and Professor Geckner. But they're sort of nice in that you know a bunch of things already about the real numbers. So some of the results may not be surprising, but you'll have to think carefully about, am I only using the axioms to prove this fact, right? Another nice thing is that when you take Math 402 or Math 327, where you really study the real numbers carefully, it'll be good to have a good solid foundation, an axiomatic foundation. Okay, so the first axioms tell you how the real numbers behave. The real numbers form a field, something called a field. Okay, so I'm not gonna, I mean, what a field is going to be a thing that satisfies the following axioms, but you'll learn more about these in Math 402. This is like Introduction to Abstract Algebra. But for now, all you need to know is that a field is just some set of objects in which there's some addition operation and some multiplication operation, which satisfy a bunch of properties. So for now, a field is a set of objects with two operations. Addition. So we denote this by a plus sign, and multiplication. Which we denote either A, B concatenation or A dot B. By the way, to get this in LaTeX, this is \C dot for center dot. Satisfying the following properties. So these properties tell you exactly how the real numbers behave. Well, actually, they tell you how any field behaves. So field axioms. In other words, these axioms tell you properties of addition and multiplication. Okay, so the first axiom we have is called closure. Closure under addition and multiplication. So this axiom says that if a and b are real numbers, that's our notation for that, then a plus b is a real number and a times b is a real number. This is a thing that we're allowed to assume about real numbers, that you can add two real numbers and you get a real number. You can multiply two real numbers and you get a real number. Okay, this is basic, right? So we're really starting from assuming nothing, and we're going to build up the axioms of the real numbers from nothing. This is why in our proofs we have to be really careful that we're not assuming more than we know. Okay, the second axiom is called commutativity of addition and multiplication. And it says that if a and b are two real numbers, then, right, we define this operation addition plus, but if you take a plus b and b plus a, the closure axiom tells you that those are two real numbers. A plus b is a real number, b plus a is a real number. There's nothing that says so far that those are the same real number. Right? A plus b is some real number, b plus a is some real number. But we will assume commutativity. In other words, we'll assume that those are actually the same real number. Again, a property very familiar to you from the real numbers, but a thing that we're going to assume about them. Okay, and also we'll assume that multiplication is commutative. What I'm trying to make the point here is, before we state this axiom, if you write down a plus b and you write down b plus a, we don't know that those are the same thing. Now that we have this axiom, we do know that they're the same thing, and we can use this axiom. Okay, the third axiom is called associativity, again, of both multiplication and addition. So if you have three real numbers, then a plus b plus c is the same thing as a plus b plus c. Again, let me point out that this is a thing that we need to assume. One tricky thing about this is that you've been using stuff like this for almost your entire life at this point without thinking about it. Now I'm asking you to think about it. Okay, so we're assuming closure and we're assuming commutativity. So before this axiom, like a plus b, we know that this is some real number, which is the same thing as b plus a, right? And then if you take that real number and you add it to c, then again, by the first axiom, this is some real number. On the other hand, b plus c, that's some real number, which is the same thing as c plus b. You add it to a, that's some other real number. But there's nothing that we've assumed so far that says that these are the same real number, right? But now that we're assuming associativity, anytime you see the quantity a plus b plus c, you could say, well, by associativity, this is the same thing as a plus the quantity b plus c. Okay, and of course, also associativity of multiplication is another thing that we assume. Okay, so we'll assume that we have two operations that are commutative and associative. Okay, the fourth axiom is called distributivity. And distributivity is an axiom that tells you how addition and multiplication interact with one another. Right, so these first three axioms were just a statement about addition and a separate statement about multiplication. So it just said, this is how addition works, this is how multiplication works. The distributivity axiom explains how addition and multiplication interact with one another. So if a, b, c are three real numbers, then if you take a times the quantity b plus c, so you take the real numbers b plus c and you get another real number. I mean, you take the real numbers b and c, you add them, you get another real number, you multiply that by a. This is the same thing as multiplying a by b, multiplying b by a by c, and then adding the result. Again, a priori, there's no reason that these two numbers should be related, except that we're assuming it as an axiom. Okay, and also, so this is like distributivity on the left. We can also assume this, which probably you can actually prove from just using commutativity. But we may as well assume it here. So anytime we want to distribute, it doesn't matter which side we distribute over. Okay, 5. the fifth axiom is the existence of identities. Okay, so here what we'll assume is we will assume that, okay, so by the way, notice so far I haven't even assumed that there are any real numbers that even exist yet. All I've said that is if A and B are real numbers, then you can add them and you can multiply them and they satisfy these properties. But we don't even know of any real numbers at this point, which kind of makes sense because there are other fields that aren't the reals that satisfy all of these axioms, but they aren't, the sets of objects are not odd numbers. So there's nothing here that says that these are numbers yet. But here we'll assume that there are two different real numbers that we'll call 0 and 1. Okay, so here I'm assuming the existence of two objects in my set, such that for all real numbers A plus 0 equals A, and A times 1 equals A. So here I'm assuming the existence of two real numbers that have this property of being the additive identity and the multiplicative identity. Okay, 6 is the existence of additive inverses. So for every real number A, there exists some other real number, which I'll call negative A, such that if you add A and negative A together, you get 0. Okay, so I'm assuming anytime you have a real number, there is some other real number, which, by the way, could be the same real number, right? So, but I'll call it negative A, that has a property that if I add it to A, I get this additive identity that I assumed existed in axiom 5. Okay, and finally, multiplicative inverses. Here I'm going to assume for all, I'll leave a space here, or actually let me add something. For all real numbers A, I'll leave a space here. There exists a real number which I'll call A inverse, such that A times A inverse equals multiplicative identity. I guess I don't need parentheses here. Okay, hopefully you've figured out what goes in the blank here, because currently this axiom is not true for the real numbers, because 0 does not have a multiplicative identity. Sorry, a multiplicative inverse. Right? The additive identity does not have a multiplicative inverse. So for all A and R such that A is not equal to 0, every non-zero number has a real number has a multiplicative inverse. Okay, so these axioms are what we're allowed to assume from the start about addition and multiplication of real numbers. Okay, I'll also say that if we're also allowed to assume axioms 1 through 5 for the natural numbers. So let me just note that here. So in other words, you're allowed to assume that the naturals have closure, commutativity, associativity, distributivity, and identities. Notice though that I'm being a little bit loose here. So for the first axiom, for example, if I'm doing this for n, it should say if A and B are real or natural numbers, then A plus B is a natural number and AB is a natural number. So when I say you can assume the first 5 axioms for the natural numbers, you of course have to change them so they're quantified over n. Okay, for the integers, we can assume will satisfy the first 6 axioms. Right, and then we're also allowed to assume that the rational numbers satisfy all 7 of these axioms. Okay, so these axioms we're allowed to assume for the real numbers, but the first 5 I can assume for naturals, the first 6 I can assume for integers, and I can also assume these all for the rational numbers. This is because the rational numbers are also a field. The reals are not the only field. These axioms just say that the real numbers are a field. Okay, which means that we must need more axioms to actually define the real numbers, right? Because right now, if I just assume these 7 things, I could be talking about the reals, I could be talking about the rationals, I could be talking about actually there are infinitely many different fields. So we'll see that we'll need more axioms. But these ones govern how addition and multiplication relate to one another. Okay, just some notation for these things. So for 2 real numbers a and b, we may denote the following thing. So if you take a, you take the additive inverse of b, which exists by axiom 6, and you add them together by closure by axiom 1, that's a real number. I will denote this thing sometimes by a minus b. Okay, notice I haven't defined, before now, I haven't defined subtraction. But now I'm defining what I mean by a minus b. I mean, you add together a to the additive inverse of b. Okay, so these tell you about addition and multiplication of real numbers and actually all of our number systems. The next set of axioms that we'll assume are axioms that have to do with equality. Okay, so next, equality axioms. Okay, and I should say that these axioms are not just for the real numbers, but any notion of equality. So these are for any notion of equality. Okay, so for example, we defined what it meant for 2 sets to be equal. So here I'm going to write down a bunch of axioms for this notion of set equality as well. Okay, but I'll keep the numbering. So like I'll keep the numbering following what we did before, because again, if you take a look at the sheet, on your homework or on your exam, you might say, oh, by axiom 9, I can do this, right? And therefore, all of these have their own number, so you can uniquely identify them by number. Okay. So axiom 8 is called reflexivity. It says this: for every real number a equals a. So again, one issue with learning things from the basics is it seems like I've written something so obvious that it seems almost kind of absurd, right? Why do I need to assume that a equals a? It's because here what I'm really defining is what we mean by the word and the symbol equals. We need to start from somewhere, so we need some notion of equality. Equality satisfies some axioms. I'm trying to lay out exactly what those are. Okay, but as I said, this is for any notion of equality, so you can also say for any set, capital A, it equals itself. That's the thing that you're allowed to assume by reflexivity of equality. Okay, 9 is a property called symmetry. So for all A, B, and R, if A equals B, then B equals A. Again, this is a property of this notion of equality. If the real number A is equal to the real number B, then I'm going to assume that the real number B is equal to the real number A. Okay, 10 is called transitivity, which is for any real numbers A, B, C, if A equals B and B equals C, then A equals C. Okay, and then the final equality axiom is called the substitution axiom. It says this: for all real numbers A and B, if A equals B, so if at some point you know that A is equal to B, then B may be substituted for A in any number of places within a mathematical statement without changing the truth value of that statement. Right? So for example, if you know that A equals B and A is even, then you know that B is even because A equals B. How do you know that? Because in your mind, you already know the substitution axiom. If you have two equal things, then if something is true about the first thing, it must be true about the second thing. Okay, so again, as I said before, these hold for, I've stated them only for real numbers, but they hold for natural numbers, integers, right? In other words, if A and B are integers and A equals B, then also B equals A. If A and B are sets and A equals B, then B equals A. So this is actually for any notion of equality, you're allowed to use these four axioms. Okay, so at this point in the class, these are the only things that we're allowed to assume and use in proofs. So this is square one, ladies and gents. At this point, we may only assume definitions and axioms 1 through 11. We're going to build up a bunch of mathematics just from this ground floor of these 11 axioms and definitions. Of course, as we prove more and more things in the course and in problem sets, the knowledge we'll have will grow. So by the end of the course, we'll be proving much more complicated statements, but we'll know that it's on a solid foundation because we started from the axioms. Okay, so one very common type of problem that will occur on many problem sets and on your exams will be proving things directly from the axioms. So let me give you some examples. Okay, so this will be our first theorem that we're really truly proving without assuming anything. Again, I can't make this point enough. You need to justify every step that you're only assuming the axioms. So this means that there are many things that you think are obvious, but they need to be proved if they're not axioms. So let's call this our first theorem, baby's first theorem. We're all babies at this point in the course. So let A, B, and C be real numbers. If A equals B, then AC equals BC, and A plus C equals B plus C. Okay, again, the danger of being a math major is that you write things like this down and your roommate who's not a math major thinks, what the heck is my roommate doing? Like, this is a thing that I've known my entire life. The point is that if you don't think carefully about this from the axiom, you actually don't really know the statement your entire life. You're sort of just assuming the statement. But it seems so natural, right? It seems like this is the kind of thing that we should just be able to use. But the point of this part of the course is to build everything up from just the axioms. And this is not an axiom of the real numbers, which means that's a statement that we need to prove. Okay, I notice that this is a statement of the form if P, then Q, which means that we can prove it directly by assuming P, making some deductions, and then showing that Q must hold. This is our method of direct proof. Okay, so here's our proof. And again, I need to go directly from the axioms. Okay, so I get to start by assuming P. Okay, so a good thing to start your proofs with is always lay out all your notation and your assumptions. Okay, so let A, B, C be real numbers, and suppose that A equals B. By the technique of direct proof, if I can make a sequence of deductions using only things that I know, and I can show that AC equals BC and I can show that a plus c equals b plus c, then I have proved this theorem. So let's do this. Okay, so I want to understand first AC and BC. I want to show that they're the same thing. Well, what is AC? It's a real number, but I only know that by the closure of the reals, right? That's axiom 1. If A and C are real numbers, then AC is a real number. So by closure of the reals, AC is also a real number. I want to try to show that AC equals BC. How the heck can I do this? Well, this must need to use one of my axioms of equality, right? Because what I'm starting with is A equals B. I must have to use some equality axiom somewhere to get the AC equals BC. Okay, well, now that I know that AC is a real number, by reflexivity of equality, I know that AC equals AC. That's good. That's not AC equals BC, though. But at least I've introduced an equality into the room. But now I get to assume that A equals B, which means that I can use the substitution law to substitute B any number of times into any mathematical statement. And that's true, and it's still true. So then by the substitution law, or by the substitution axiom, we may substitute B for A on the right-hand side of the equality, because that's a mathematical statement. To deduce that AC equals BC, right? Since AC equals AC was true, if I substitute B for A, I don't change the truth value, therefore AC equals BC is true. Okay, now, similarly, by closure, A plus C is also a real number. By reflexivity, A plus C equals A plus C. And so by substitution, A plus C equals B plus C. So what have I shown? I've shown that AC equals BC is true. I've shown that A plus C equals B plus C is true, assuming that A equals B. So since I've shown that this is true and this is true, this means that the conjunction AC equals BC and A plus C equals B plus C is true. Therefore, I've shown that Q is true. Hence, AC equals BC and A plus C equals B plus C as desired. And then I end my proof with a box. Okay, so let's talk about this proof for just a second. So first of all, notice that this proof is written in complete sentences in English, because that's the language of this course. So there are periods, there's punctuations, there's no fragments. There are some mathematical symbols that are allowed in a proof. So for example, if I say A equals B, I'm allowed to write that as part of a sentence. I'm also allowed to use the symbol R for the real numbers and the symbol element of to say that something is an element of something. Okay, but I didn't, for example, I didn't use the symbol, this wedge symbol for and here because that's a logical operator symbol, but here I'm trying to write a sentence. Okay, also notice that I carefully justified why every statement was true only by using stuff that I know is true. So I've said what axiom I'm using. There's no jumps in logic here. And then I tried to be extremely clear so that you all understand what I'm saying. So that if you have this list of axioms, you can follow along and realize, oh yeah, this is true. So the kind of thing that you should shoot for is when you write a proof, can somebody else in the class, some other student, read my proof, understand what's happening the entire time? Okay, also, the most customary symbol to end your proof with is a box, but you can end your proof however you want. So you could choose another picture, for example. You could end all your proofs with a smiley face if you want. You can end all your proofs by writing QED, which is Latin for quod erat demonstratum, that which was to be demonstrated. Or in French, CQFD, c'est qu'il faut démontrer. There's a German one too, which is like, oof, I should just know it. Luckily, since this is the magic of the internet, I can just look it up. There's even a whole Wikipedia page. Can I do this? There's QEF, quod erat faciendum. There's I can't find the German one. But in English, there's also, you could do www or w to the fifth, which was what we wanted. There are many things that you can put here. So the most boring one, with the ergo the one that I use, is just a box. But it's also the one that automatically gets done in LaTeX. But you can customize your LaTeX to end proofs with another symbol. So if you want to figure out how to do that, I encourage you to play around with it. Okay, also another thing that I should mention about this proof is that this proof is this theorem is going to be extremely useful for us. There will be lots of times where we'll have A equals B and we'll want to say, oh, A plus C equals B plus C. That's not an axiom, but now that we've proved it, it's like I could take this, I can put it in a black box, and I'm now allowed to use this black box later on. So I'll say, oh, in your notes, this is theorem 38. So if we're going to give it a theorem number, I can say, oh, by theorem 38, since A equals B, A plus C equals B plus C. Now I don't need to go through this whole rigmarole just to use that very basic fact. Right? And if you think back to like linear algebra, there were tons of times when, in order to prove something, what you do was you added the same vector to both sides. That was really using this theorem. Okay, let's now get our second theorem, which is called, I'll give this one a name. So in your notes, this is theorem 39. This is called the cancellation law. It says the following. If A, B, and C are real numbers, such that A plus C equals B plus C, then A equals B. Again, if you show this to your roommate, you're in danger of looking like a fool, right? Like, oh, obviously I know that's true. But it's not an axiom. So if you're building up the real numbers from the ground floor, we don't know that this is true yet. Also notice that this is actually not true for multiplication. So you might be tempted to say, oh, well, if AC equals BC, then A equals B. But this is not true because of the real number C equals 0. So maybe it's not so obvious, right? I should say that since the real number C equals 0 matters for the multiplication, this suggests that maybe what we need to use in order to prove this is to use some kind of additive inverse thing, because 0 doesn't have a multiplicative inverse, which could explain why the second statement fails while the first statement is true. Because amongst the things that we've assumed about the addition and multiplication, they've been very similar so far. Okay, so let's prove this totally carefully. Again, we start proofs by writing the word proof, and we should lay out what we're assuming, and then we're going to deduce what we want at the end. Okay, so let's suppose that A, B, and C are real numbers such that A plus C equals B plus C. Right, again, this is a statement of the form if P, then Q. So I get to assume P, I just need to show that Q is true. Okay, well, what's the thing that you want to do here? We should think, mathematics is all about ideas, right? Mathematics is not about just pushing symbols around meaninglessly. And I think the idea behind this proof is not so hard. What you do is you want to subtract C from both sides to show that A equals B. That's what you want to do. But we need to figure out how to do this using only the axioms. Okay, so if I want to subtract C from both sides, really what I want to do is I want to add the additive inverse of C to both sides. So by the existence of additive inverses, I know that negative C is a real number. There's some real number that serves as the additive inverse of C. Now I want to add it to both sides. Luckily, our first theorem says that I can add C to both, negative C to both sides of an equality and get a true statement. And so by the previous theorem, so I'll call it theorem 38, what does it say? The previous theorem says that if you have two things that are equal, you can add any real number to both sides and maintain equality. Right? So here I have two real numbers that are equal, and I can add this real number to both sides. So by theorem 38, A plus C plus negative C equals B plus C plus negative C. You notice here that here I need parentheses because we're building up the real numbers from the very foundations. So here I mean you add this real number to this real number. So I need parentheses to show that that's what I mean. Okay, and here I'll put a period to end the sentence. Okay, now using the associativity axiom, we have what? A plus C plus negative C is equal to, I can reassociate this, C plus negative C. Similarly, B plus C plus negative C equals B plus C plus negative C. Okay, now what I can do is I can use the substitution axiom twice, right? I can substitute this expression in for this expression here, and I can substitute this expression in for this expression here without changing the truth value. So by the substitution, A plus C plus negative C equals B plus C plus negative C. Okay. Now, C plus negative C, that's 0 by our definition of additive inverses, by our additive inverse axiom. Okay, so since negative C is the additive inverse of C, C plus negative C equals 0. Okay, here I'm going to take the first shortcut in the class, which you are now all allowed to use, which is I'm going to freely allow you to substitute into equations. So here, I'll say by substitution, A plus 0 equals B plus 0. right? In other words, I'm substituting in c plus a gives c in for 0 twice. But I'm just going to say by substitution. Okay, I guess I sort of did the same thing previously. Okay, and now a plus 0, that's just a by the additive identity. B plus 0, that's just b by the additive identity. So by the additive identity axiom, a plus 0 equals a, and b plus 0 equals a. So again, by substitution, a equals b, which is what we wanted to prove. Okay, so as you can see, these proofs involve you really being careful about what you're assuming, not ever using more than the things that you actually know. Very quickly, this is going to become a bit tiresome. So like when we're trying to understand more complicated things, we'll learn stuff about, I don't know, divisibility, functions, all kinds of crazy stuff in this class. It's going to be a bit annoying if we want to justify everything by the axioms every single time. So later on in this class, we're not going to be this particular and careful on every single proof. Things like adding c to both sides, we'll just sort of say, oh, you can add c to both sides, just as an example. But for some problems, I will ask you to prove things directly from the axioms because you should be able to do it. But when we want to talk more complicated things, we're going to assume sort of a lot more things because I'll assume that you know how to prove carefully from the axioms if you needed to. What I'm trying to say is there will be sort of a distinction between problems that ask you to prove things directly from the axioms and problems that don't ask you to prove things directly from the axioms, in which case you can sort of assume more without worrying too much. But for now, what we're working on is this particular skill. So you want to be extremely careful and extremely thorough in proofs of this kind. Okay, so in the next lecture, we will continue proving things from the axioms. And in fact, we'll even learn pretty quickly some new techniques and some new axioms. Okay, so I think I'll stop this lecture here, and we'll essentially continue with 3.1 and real number axioms in the next lecture.